Okay, so today we're diving into this paper titled MOBA, Mixture of Block Attention for Long Context LLMs.
Sounds fun.
It's a pretty dense one.
Yeah.
But I think the insights are really worth it, especially if you're working with large language models and want them to be able to handle long context efficiently.
For sure.
Yeah, and the authors are from Moonshot AI, Single University, and Zichang Lab.
Nice.
And they're tackling this, big problem of how do we scale context length in LLMs without, the computational costs going through the roof.
Yeah, it's a huge problem.
And they argue that current solutions like, sync or window attention, linear approximations, all these things either sacrifice performance or require building completely new models.
Right.
So their proposal is MOBA, which is a new architecture that really cleverly applies this mixture of experts principle to attention itself.
That's cool.
Yeah, so instead of attending to all tokens, MOBA kind of lets the model dynamically select the most relevant blocks of past information for each query.
I see.
So it's like instead of reading a 1,000-page book word by word to find the answer, you have this, super smart research assistant who just pulls out the right books for you.
Yeah, that's a great analogy.
So we can jump into like a little summary, I guess, for the first minute.
Okay, cool.
So basically, researchers have developed this new attention mechanism called MOBA, which allows large language models to process longer sequences of text way more efficiently.
Okay.
And MOBA partitions the context into blocks and uses a gating mechanism to selectively route query tokens to the most relevant blocks.
Gotcha.
So this reduces the computational cost of attention, enabling LLMs to handle longer contexts without, sacrificing performance.
Yeah, cool.
So back to the paper, it's like having a super smart research assistant who just pulls out the right information instead of having to wade through everything.
Yeah, exactly.
So I guess the first thing to understand is how MOBA partitions the input sequence into these blocks of tokens, right? It's kind of like chapters in a book.
Exactly. Each block is like a chunk of the context, and MOBA allows the model to focus on just a handful of these blocks.
Okay, but how does it decide which blocks to focus on?
That's where the gating mechanism comes in.
Okay.
So for each query, MOBA calculates an affinity score between the query and each block.
Uh-huh.
And it's like measuring how relevant a chapter is to the research question you're trying to answer.
Oh, okay, I get it.
Right, so the higher the score, the more relevant the block.
So like if I'm researching someone's childhood, the chapter about their early life is going to be more important than like their later career.
Exactly. And the gating mechanism uses these scores to select the top K blocks, meaning only a small subset of the context is used for attention calculation.
Oh, okay.
Which really reduces the computational burden.
So instead of reading the whole book, we're just reading the most relevant chapters.
Exactly.
But what about causality? I mean, LLMs generate text one token at a time. We need to make sure that MOBA doesn't peek into the future.
Right, totally. Causality is critical in language modeling.
Yeah, we can't have the model like predicting a word based on words that come after it.
Like reading the ending of a book before you start it.
Exactly.
Yeah, so to ensure causality, MOBA incorporates a couple of mechanisms.
Okay.
First, it restricts attention to past and current blocks, so it prevents the model from looking ahead.
So no spoilers?
Haha, no spoilers allowed.
What's the second mechanism?
So it handles the current block with special care.
Okay.
The current block is the one containing the query token, and MOBA applies a causal mask to make sure that that token can only attend to previous tokens within its own block.
Right.
So that maintains that strict sequential order.
Okay, that makes sense.
So we have these blocks and the smart system for choosing the worthy ones.
Right, and keeping things causal.
Yeah, exactly. But now it gets interesting when we talk about the practical side of things. How do we implement MOBA, and how does it compare to traditional attention in terms of efficiency?
Yeah, I'm curious about that too.
So they've actually managed to integrate MOBA with techniques like flash attention and MO optimizations to create this really high-performance implementation that can be integrated into existing transformer models.
So no need to reinvent the wheel.
Exactly.
So what about speed? I mean, how much faster are we talking?
Their experiments show that MOBA can achieve significant speedups compared to full attention, especially as the sequence length increases.
Okay.
Like, for example, when pre-filling a sequence of 1 million tokens, MOBA was up to 6.5 times faster than traditional attention.
Wow, that's a pretty significant speed boost.
It is, but speed is only half the story. Does MOBA actually deliver on its promise of maintaining accuracy while handling these long contexts?
Right. Does it actually work?
That's the million-dollar question. And to answer it, they conducted a series of experiments to evaluate MOBA's performance, and I have to say the results are really promising.
Okay, let's dive into those experiments then.
Okay.
First up, they looked at something called scaling laws. They trained language models of varying sizes using both MOBA and full attention, following the chinchilla scaling law. And this allowed them to compare the performance of the two attention mechanisms under controlled conditions.
Right.
So what did they find?
Well, as you can see in Figure 3A of the paper, the validation loss curves for MOBA and full attention are really similar.
Okay.
Even with MOBA's sparse attention pattern, it's essentially keeping banks with full attention in terms of overall performance.
So even with a reduction in computational cost, it's still holding its own.
Yeah, it's impressive.
But they didn't stop there. They wanted to test MOBA in these long context scenarios, right?
You got it.
So to aside MOBA's long context capabilities, they focused on what they call trailing LM loss, which is the LM loss of the last few tokens in a sequence.
Right.
Why the last token specifically?
It provides crucial insights into the model's ability to handle long-range dependencies and generate coherent text, even after processing a large amount of information.
Okay, so how did it perform?
They increased the maximum sequence length to 32K, which led to an even sparser attention pattern for MOBA up to 95.31%.
Wow.
And while MOBA did show slightly higher trailing LM loss compared to full attention, the gap progressively narrowed as the model scaled.
Oh, so its ability to handle those long-range dependencies is actually improving as the model gets bigger.
Exactly.
That's promising. But they didn't just look at loss curves, right? They took MOBA out for a spin on some real-world tasks.
Oh yeah, absolutely. They wanted to see how well it performs when it's out in the wild dealing with complex real-world data.
Okay, so tell me, how do they put MOBA to the test?
So to really push MOBA to its limits, they trained a model called Llama-8B-1M MOBA.
Okay.
And they started with a Llama 3.18B base model and gradually increased the context length all the way up to 1 million token.
1 million tokens, wow.
Yeah, it's pretty impressive.
Did they need a whole data center for that?
Well, they used some clever techniques like position interpolation to ease the transition to longer contexts, and they activated MOBA for 100 billion tokens during the training process.
Okay.
So this allowed them to achieve an impressive attention sparsity of 95.31%.
Okay, so they trained this model with super long contexts, but how did they evaluate its performance on real-world tasks? What kind of benchmarks did they use?
They used a variety of benchmarks designed to test language models in long context scenarios.
Okay.
Importantly, they used MOBA for prefill, which is where the model processes the initial context but switched to full attention during the actual generation of text.
Oh, interesting.
Yeah.
Why the switch? If MOBA is so efficient, why not use it for the whole process?
So it turns out that while MOBA excels at efficiently processing massive amounts of information using full attention for generations, produced slightly better results in their tests.
I see.
So this hybrid approach seems to strike the best balance between efficiency and performance.
Okay, that makes sense.
Yeah.
So how did this hybrid MOBA model stack up against a full attention model trained in the same way? Were they able to achieve comparable results?
The results are really compelling. You can find them summarized in Table 2 of the paper.
Okay.
And across a range of benchmarks, including AGVAL, BBH, CVAL, and even the very demanding Ruler benchmark, which uses a context length of 128K tokens, Llama-8B-1M MOBA achieved scores that were nearly identical to the full attention model.
Wow, so we're talking comparable performance even when MOBAs operate with a sparsity of 62.5% on Ruler.
Exactly.
That's a massive reduction in computational costs without sacrificing accuracy.
Yeah, it's really impressive.
It shows that you can have your cake and eat it too.
Haha, right.
You can have the efficiency of MOBA without compromising on the quality of the output.
Exactly.
But they didn't stop at 128K tokens. They wanted to see how the model handled even longer contexts, so they turned to the needle in a haystack benchmark.
Yeah.
Needle in a haystack.
It's kind of what it sounds like.
Okay.
It tests the model's ability to find a specific piece of information within a massive amount of data.
Okay.
In this case, they pushed the context length all the way up to 1 million tokens.
So like finding a needle in a haystack 1 million tokens long.
Pretty much.
Okay.
And as shown in Figure 7, even with this extreme context length, Llama-8B-1M MOBA performed admirably.
Okay, so MOBA is clearly capable of handling these super long contexts, and it's performing on par with full attention in benchmarks.
Yeah.
But let's circle back to efficiency for a moment.
Sure.
We saw some pretty impressive speedups earlier, but how does MOBA's computational cost actually compare to full attention as the sequence length grows?
That's a great point.
Yeah.
To get a sense of MOBA's efficiency, they compared the forward pass time of the attention layer in both the MOBA model and the full attention model as they scaled the sequence length.
Okay.
And all other layers in the models were identical, so this was a direct comparison of the attention mechanisms themselves.
Right.
And as you can see in 22A, MOBA consistently outperformed full attention across all context lengths, demonstrating subquadratic computational complexity.
Okay, so as we discussed earlier, it achieved a 6.5x speedup with 1 million tokens. But what's even more impressive is that when they pushed the sequence length to 10 million tokens, hold on, 10 million tokens.
Yeah.
How is that even possible?
It's pretty mind-blowing.
Yeah.
They expanded the use of Tensor Parallelism to distribute the computation across multiple GPUs, allowing them to tackle these massive sequences.
Okay.
And even at this extreme scale, MOBA achieved a remarkable 16x speedup compared to full attention.
Wow, that's really incredible.
It is.
So MOBA isn't just capable of handling these incredibly long contexts, but it's also significantly faster than traditional attention.
Right.
This could be huge for applications that require processing massive amounts of text or code.
Totally agree. And this efficiency comes from a combination of factors. The block sparse attention mechanism, the integration with techniques like flash attention, and the optimized implementation that leverages both MOE and distributed computing techniques.
So it's like they've created a super efficient engine for language models.
Yeah, I like that analogy.
But I'm curious, they mentioned having to make some adjustments to get MOBA to work well during supervised fine-tuning.
Yeah.
Can you explain that a bit? What were the challenges?
They found that MOBA sometimes struggled during supervised fine-tuning because of loss masking.
Loss masking.
Yeah, so basically during supervised fine-tuning, certain tokens in the input, like propped tokens, are excluded from the loss calculation.
Right.
And this can create problems for sparse attention methods like MOBA because the backpropagation of gradients can be hindered by the masked tokens.
So it's like trying to train the model on a text with some parts blacked out, and MOBA struggles because it's missing information.
Exactly, like trying to solve a puzzle with some pieces missing.
So how do they solve that problem?
So they came up with this really clever solution called layer-wise hybrid,
Okay.
where during fine-tuning, they switched the last few layers of the model from MOBA back to full attention.
Oh, interesting.
So it's like giving the model a bit of full vision towards the end of the process.
To help it learn from the masked data.
Right, and as shown in figures 5b and 5c, this layer-wise hybrid approach significantly reduced the fine-tuning loss, demonstrating the adaptability and practicality of MOBA in different training scenarios.
So we've covered a lot here.
We have.
We've seen how MOBA works, its impressive efficiency gains, and its ability to handle incredibly long contexts while maintaining accuracy.
Right.
It's clearly a very promising approach. But before we wrap up, I want to get your take on something that's been on my mind.
Okay, what is it?
They focus a lot on the how of MOBA, the block selection, the gating mechanism, the efficiency.
Right.
But I'm also curious about the what. Like, what kind of knowledge is the model actually retaining and using with this block-based attention? Does selectively attending to certain blocks of information change the way the model thinks about the context?
You're raising a really interesting question.
It makes sense that we'd see performance gains from focusing on the most relevant information, but is there a risk that we're shaping the model's understanding in ways we haven't fully grasped?
It's definitely something to consider. Like, if the gating mechanism consistently prioritizes certain types of blocks over others, it's possible that the model might develop blind spots or exhibit biases towards certain information patterns.
Right. So, for example, if the gating mechanism tends to favor recent blocks over those further back in the sequence, could that lead to a kind of recency bias where the model overemphasizes the most recent information?
It's a plausible scenario, and it highlights the need for further research into the long-term effects of MOBA's block selection strategies on the types of knowledge representations the model forms.
This isn't just an academic concern either, right? If we're building LLMs that can reason and problem solve in complex real-world situations, we need to be very aware of the potential biases that might be baked into their attention mechanisms.
Absolutely. Understanding how these selective attention mechanisms influence a model's knowledge acquisition and reasoning processes is critical, especially as we move towards deploying these models in more sensitive and high-stakes applications.
So what does this all mean for our viewers who are working on the cutting edge of LLM development? What key takeaways should they be thinking about as they explore MOBA and other long context models?
I think MOBA offers a really promising path towards building more efficient and scalable long context LLMs.
Okay.
It's compatible with existing models, delivers impressive performance gains, and opens up exciting possibilities for handling the massive amounts of data needed for complex reasoning.
Right.
It's a real step forward in the field.
But as with any powerful tool, we need to use it responsibly.
Absolutely. We need to be mindful of the potential implications of these selective attention mechanisms and conduct rigorous research to make sure that we're building LLMs that are not only powerful, but also fair and unbiased.
Okay, I think that's a great point to end on.
Yeah.
This paper has given us a lot to think about.
Definitely.
Not just in terms of the technical advancements, but also the broader ethical considerations of building increasingly sophisticated AI systems.
Right.
Huge thanks to our expert for guiding us through this deep dive into MOBA.
It was my pleasure.
And to our viewers, keep those questions coming and those minds exploring.
Yeah, keep learning.
Until next time.
See ya. So as the models get bigger, their ability to handle those long-range dependencies is getting better.
Yeah, that's really promising. But they didn't just look at, loss curves.
Nope.
They took MOBA out for a spin on some real-world tasks.
Absolutely. They wanted to see how well it performs when it's out in the wild, dealing with complex real-world data.
Right. Okay, so tell me, how did they put MOBA to the test? What kind of challenges did they throw at it?
So to really push it to its limits, they trained this model called Llama 8B1M MOBA.
Okay.
So they started with the Llama 3.1 8B base model.
Okay.
And they gradually increased the context length all the way up to 1 million tokens.
1 million tokens?
Yeah.
That's pretty wild.
It's pretty impressive.
Did they need like a whole data center for that?
Well, they used some clever techniques like position interpolation to help with the transition to longer contexts.
Okay.
And they activated MOBA for 100 billion tokens during training.
Okay.
And that allowed them to achieve an attention sparsity of 95.31%.
Okay, so they trained this model with super long contexts, but how did they evaluate its performance on real-world tasks? What benchmarks did they use?
They used a variety of benchmarks that are specifically designed to test language models in long context scenarios.
Okay.
And importantly, they used MOBA for what's called prefill, where the model processes that initial context, but then they switch to full attention during the actual generation of text.
Interesting. Why the switch? If MOBA is so efficient, why not use it for the whole process?
So it turns out that while MOBA is really good at efficiently processing massive amounts of information, using full attention for generation produced slightly better results.
Okay.
So this hybrid approach seems to be like the sweet spot between efficiency and performance.
That makes sense.
Yeah.
So how did this hybrid MOBA model stack up against a full attention model trained the same way? Were they able to achieve comparable results?
The results are really compelling. You can see them in Table 2 of the paper.
Okay.
Across a range of benchmarks, AGVL, BBH, CVL, and even that really demanding ruler benchmark, which uses a context length of 128K tokens, Llama 8B1M, MOBA achieved scores that were almost the same as the full attention model.
So we're talking comparable performance, even when MOBA's operating with a sparsity of 62.5% on ruler?
Yeah.
That's pretty amazing. I mean, that's a massive reduction in computational costs without sacrificing accuracy.
Yeah, it really is impressive. It shows that you can have the efficiency of MOBA without having to give up the quality of the output.
For sure. But they didn't stop at 128K tokens.
Nope.
They also wanted to see how the model handled even longer contexts. So they used this benchmark called needle in a haystack.
Right.
Needle in a haystack. What's that?
So it tests the model's ability to find a specific piece of information in a huge amount of data.
Okay.
And in this case, they pushed it all the way to 1 million tokens.
So it's like literally finding a needle in a haystack, but like digital and 1 million tokens long.
Pretty much.
Okay.
And as shown in Figure 7, even with this crazy context length, Llama 8B1M MOBA still did a great job.
Wow, so MOBA's clearly capable of handling these super long contexts and is performing really well compared to full attention.
It is.
But let's go back to efficiency for a second.
Okay.
We saw those impressive speedups earlier, but how does MOBA's computational cost actually compare to full attention as that sequence length grows?
That's a great question. So to really understand MOBA's efficiency, they compare the forward pass time of the attention layer in both the MOBA model and the full attention model as they scaled that sequence length.
Okay.
And they kept all the other layers in the models exactly the same. So this was a head-to-head comparison of just the attention mechanisms.
Okay, cool.
And the results are in Figure 2A.
Yep.
MOBA consistently outperformed full attention across every context length, showing that subquadratic computational complexity.
Right, and as we were saying earlier, it was 6.5 times faster with 1 million tokens. But it gets even crazier when they pushed the sequence length to 10 million tokens. Hold on, 10 million tokens?
Yeah,
How?
it's pretty mind-blowing.
Yeah.
They used Tensor Parallelism to distribute the computation across multiple GPUs,
Okay.
which let them handle these huge sequences, and even at that scale, MOBA was 16 times faster than full attention.
Wow, that's really something else.
It is.
So MOBA can handle these incredibly long contexts, and it's also way faster than traditional attention.
Exactly.
This could be a game changer for applications that need to process tons of text or code.
Absolutely. And this efficiency comes from a few things: the block sparse attention, the integration with flash attention, and the optimized implementation that uses both Mo and distributed computing.
It's like they've built this super efficient engine for language models.
Yeah, I like that analogy.
But they did mention having to tweak some things to get MOBA to play nice during supervised fine-tuning.
They did.
What were the challenges there?
So they found that MOBA sometimes had trouble during supervised fine-tuning because of loss masking.
Loss masking.
Yeah, so during supervised fine-tuning, some tokens in the input, like those prop tokens, are left out of the loss calculation.
Right.
And that can cause problems for sparse attention methods like MOBA because the backpropagation of gradients gets messed up by those masked tokens.
So it's like trying to train the model on a text where some parts are blacked out.
Right.
And MOBA struggles because it doesn't have all the information?
Exactly, like trying to solve a puzzle with missing pieces.
Okay, so how do they fix that?
They came up with a pretty cool solution called layer-wise hybrid.
Okay.
During fine-tuning, they switched the last few layers of the model from MOBA back over to full attention.
Oh, interesting.
Yeah, so it's like giving the model a bit of full vision towards the end.
To help it learn from that masked data.
Exactly, and it worked really well. As you can see in figures 5b and 5c, this layer-wise hybrid approach significantly reduced the fine-tuning loss, which really shows how adaptable MOBA is.
Okay, so we've covered a ton of ground here.
We have.
We've talked about how MOBA works, those impressive efficiency gains, and its ability to handle incredibly long contexts without losing accuracy.
Right.
It's a really promising approach, but before we move on, I want to get your thoughts on something that's been bugging me.
Okay, what's up?
They talk a lot about how MOBA works, the block selection, the gating mechanism, all that stuff.
Yeah.
But I'm curious about what kind of knowledge the model is actually holding on to and using with this block-based attention. Does picking and choosing certain blocks change how the model thinks about the context?
That is a really interesting question.
It makes sense that we'd see performance gains from focusing on the relevant information, but are we maybe shaping the model's understanding in ways we don't fully get?
It's something to think about for sure.
Yeah.
Like if the gating mechanism always prioritizes certain types of blocks, maybe the model could develop blind spots or biases toward certain information patterns.
Right, so like what if it always favors recent blocks over older ones? Could that create a recency bias?
That's definitely possible, and it shows why we need more research into the long-term effects of MOBA's block selection strategies on how the model builds knowledge.
This is important stuff, right? I mean, if we're building LLMs that can reason and solve problems in the real world, we need to be really careful about potential biases in their attention mechanisms.
Absolutely. Understanding how these selective attention mechanisms shape a model's learning and reasoning is super important, especially as we start using these models in more sensitive applications.
So for our viewers out there who are working on LLMs, what are the key takeaways here? What should they be thinking about as they explore MOBA and other long context models?
I think MOBA is a really promising step towards building more efficient and scalable long context LLMs.
Okay.
It works with existing models, gives us some really impressive performance gains, and opens up all sorts of possibilities for dealing with massive amounts of data.
Right.
It's a big step forward for the field.
But like with any powerful tool, we got to use it responsibly.
Exactly. We need to be careful about the potential problems with these selective attention mechanisms and do more research to make sure we're building LLMs that are not just powerful, but also fair and unbiased.
That's a great point to end on.
Yeah.
This paper has given us a lot to think about.
For sure.
Not just about the technical side of things, but also the ethical considerations of building more and more sophisticated AI.
Definitely.
Big thanks to our expert for taking us on this deep dive into MOBA.
Happy to be here.
And to our viewers, keep those questions coming and keep exploring.
Keep learning.
We'll see you next time.
See ya.
So we've talked about all the technical stuff and how well it performs, but what about like real-world applications? Where do you see this technology actually making a difference?
Oh man, the possibilities are huge. I mean, any task that involves dealing with long sequences of information could benefit from MOBA.
Okay, so like what? Give me some concrete examples.
Sure. Think about analyzing legal documents or trying to understand complicated scientific papers or even creating personalized summaries of really long books. These are all things that LLMs have traditionally struggled with because of those context length limits.
So with MOBA, LLMs could actually understand and work with those kinds of materials.
Exactly. With MOBA, they can access and process information from way larger contexts, so they can get a much deeper understanding and produce better results.
So it could change how we use LLMs for research, analysis, you name it.
Yeah, totally. And it's not just about the length, it's also about the efficiency gains. That means we can train and use more powerful LLMs on less expensive hardware, making it accessible to more people.
Oh, that's a great point. It could really democratize access to this technology and let smaller teams do things that only big organizations could do before.
Exactly. I think we're just scratching the surface of what MOBA can do. As people keep working on it, we'll see even more amazing applications in the next few years.
It's definitely exciting to be working in this field right now. There's so much potential, and MOBA seems to be leading the way to a whole new generation of LLMs.
I agree. The possibilities are pretty much endless.
Well, I think that's about all we have time for today.
Sounds good.
We've gone over the technical details of MOBA, explored its potential, and even touched on some of the bigger picture implications.
It's been a great discussion.
Thanks so much for being here and sharing your expertise.
It's my pleasure. Thanks for having me.
And to all our viewers out there, thanks for joining us for this deep dive into MOBA. We hope you found it informative and interesting. Don't forget to subscribe to our channel for more insights into the world of AI. We'll see you next time.
See you.